Hallo, it's dumplet here. Here's an item on number theory. Find the sum of all 3-digit numbers with product of its digits equal to 10 times the sum of its digits. This item came from DAM 2022, an examination that Dumplet has hosted. The link to the PDF file will be in the description. As usual, pause this video if you'd like to give this item a try. But if you're done, let us dive into the solution. So this is one of those classic questions where we consider digits of a certain, in this case, a 3-digit number. Now, we know what we're going to do here is probably some algebra that involves the digits. Let's just say it's ABC for now. That 3-digit number is ABC. Now, typically we see a bar on the top to indicate that it's to be taken as a 3-digit number and not as a product, because this might be ABC, like a product of its digit in this case. Now, before we move on, actually, let's do some primary observation on the 3-digit numbers. I'm just gonna say the number is ABC, right? Now, the sum of its digits is obviously A plus B plus C, because we want the sum of its digits, right? And then the product of its digits is, well, obviously ABC as a product. Now, what's interesting about this one is that, well, if I try to consider another 3-digit number, let's just say CBA, which is a permutation of ABC. Now, the sum of its digits is, well, C plus B plus A. And then the product of its digit is CBA. But then again, addition and multiplication, they're both commutative. So even if I try to rearrange ABC into a CBA or any other permutation of ABC, the sum and the product of its digit will remain the same. So in fact, why not we try to find all possible triples first? So all possible triples of ABC, and then we're going to take care of the permutations after, because, well, it's going to be easier to count because it's a little bit more orderly. So our goal for now is to find all possible triples such that the sum of those three numbers is equal to, the product of those three numbers is equal to 10 times the sum of those three numbers, because that's the condition in the question. So, well, we know the product has to be ABC. The sum of its digits must be A plus B plus C. So we should be able to have ABC, product of its digits, equal to 10 times the sum of its digits, as we can see here. Now, the order doesn't matter now, so we could just kind of make some observations along the way and then just kind of simplify this Diophantine equation now, because it is technically an equation in integers. So, as with a lot of the questions on integers, technically we do have like a factor of 10 here, so on the right side, so that might be the primary attack here. So 10 is 2 times 5, obviously, so 2 times 5. Now obviously there should be a factor of 10 from ABC. Now what's more interesting is this 5 actually, because, well, A, B, or C should be a multiple of 5. Right, so one of those three must be a multiple of 5, but we know A, B, C are digits. So if it's a multiple of 5, it must be 5. So we can say from here that at least one of A, B, or C is 5. Right? We don't know which one, but we have to, we can conclude from this that one of those three numbers, the 3 digits, must be a 5. And because we did make the observation that, well, technically the order doesn't matter, so what we're going to do here is, without loss of generality, since we're just kind of finding for all possible triples, I'm just going to say A equals 5, right? Because one of them must be a 5. I'm just going to say, without loss of generality, A equals 5. I'm not saying A equals 5 all the time, but in the triple we have, at least one of them must be a 5. And that's going to help me simplify here, because from a Diophantine equation with 3 unknowns, I could just substitute A to be 5 and then just deal with the remaining thing here, right? So after substituting A equals 5, it's just technically finding the other two digits that make up the triple, containing one of the digits being 5. Okay, so we could do some cancellations here. The 5 and the 10 cancels nicely. So I'll have BC is equal to 2 times 5 plus B plus C. That's 10 plus 2B plus 2C. And just to show you guys like the standard setup for these types of questions, I'm going to move all the variables to the left side. So essentially I'll have this equation, BC minus 2B minus 2C is equal to 10. And this is actually a very typical setup. Whenever we have a BC term, a B term, or a C term, and a C term, obviously there could be other possible pairings, maybe X and Y, A and B. But generally, if we see a product and product of two variables, and then the first variable and the second variable as seen here, so B, C, B, and C, typically we would try to use the Simon's favorite factoring trick. And this is basically just factoring by grouping. Now, what do I mean by factoring by grouping here? Because, well, I could factor a B from here, from the first two terms. So I could have B times C minus 2, right? And if I were to do this by factoring by grouping, I think it would be very nice if I could factor a -2 from the C, right? Because I will have potentially a C minus 2. Now, obviously, that's not the factored form on the left side, but I'm just going to say for now it's like this, because that's pretty much how we should proceed if we're doing factoring by grouping, all right? But obviously, that's not really the factored form on the left side, so we have to kind of backtrack, I guess, and see that, well, the -2 times C minus 2, that's going to be from the -2C plus 4. Now, the -2C, we already have it. What we're missing is the plus 4. So, well, it's just a constant, so we could just easily add 4 here, right? So that's essentially the Simon's favorite factoring trick. It's just a way for us to be able to factor, and the concept is just the factoring by grouping. So like after we have this C minus 2, well, we want C minus 2 because we want to be able to factor it by grouping. So C minus 2, then times the B minus 2, and that's going to be equal to 14. Now you guys can always verify, expand this, put it back into like this format, you're going to see that it's going to be correct, all right? Now, just to keep the variables in alphabetical order, I'm just going to make it B minus 2 times C minus 2 equals 14. And this is very nice because it is a diaphantic equation, and we have the format, the left-hand side being factored, the right-hand side becoming a constant, in this case 14. And very nice setup, we could consider the factors of 14. Again, we are only interested in all possible triples A, B, C. So A is done. So B and C, again, we could interchange B and C, no problem. But again, let's just say without loss of generality, let's just say B is the bigger one. B is the bigger digit, right? Or B is greater than or equal to C. Sorry, there we go. So first we have to make the observation that B minus 2 is obviously greater than or equal to -2. And then C minus 2 is greater than or equal to -2. Now, that's assuming that both of them are, that's assuming that both of these factors, B minus 2 and C minus 2, they can be negative. Now, it can be, but if I were to see the product here, let's just say B minus 2 and C minus 2, they're both negative, right? Because, well, they multiply up to 14, so either they're both positive or they're both negative. So if they're both negative, however, they can only go as low as -2. So if both of them are negative, well, the maximum possible product is going to be 4, right? So with this, we could just easily conclude that, well, B minus 2 and C minus 2, they cannot be both negative, so they both must be positive, because obviously a positive and a negative wouldn't work because they multiply to be 14. Right? Now that's going to help me eliminate the negative cases because, well, technically we do have an integer a solution in integers. That's why we had to consider factors of 14. But then again, I could have negative ones, but thanks to this observation, I wouldn't have to consider negative ones anymore. Right, factors of 14. Well, 14 is 2 times 7, and we did make this like assumption that without loss of generality, B being greater than or equal to C. That's just going to give me two cases, 14 and 1. Again, the left factor will be bigger than the right factor because B is greater than or equal to C. So either 14, 1 or 7, 2. And we could easily solve for the B and C. B would be 16 here and C would be 3. And this would pretty much give it away that the first case here is impossible. So it can't be 14, 1. And the second one, that's going to give me B equals 9 and C equals 4. And, well, that's pretty much valid. So that's good, right? So we only have two cases. One of them doesn't give a solution. The other one, we have B equals 9 and C equals 4. So combining with the fact that we have A is equal to 5, and then from A equals 5, we have two possible values. Sorry, one pair of values for B and C, 9 and 4. And since we only wanted possible triples, there's actually only one, because what we did is, okay, we know the order doesn't matter. Let's just say one of them is 5, because it has to be, one of them must be 5. And then we realize that there's only one possible pair for the other two variables, b and c. So in fact, there's only one possible pair one possible triple for a, b, and c. And it must be 4, 5, and 9. So we could easily check like the number 4, 5, 9. That's obviously going to work. If I were to check the sum and the product of its digits, the product of its digit would be 180, the sum would be 18. And yeah, indeed, the product of its digits is 10 times the sum of its digits. But as mentioned a while ago, any permutation of the digit should also work. Now, we only have one possible triple, and it's just 3 factorial ways to arrange the digits, because we have 3 digits, obviously. So we should have 6 possible numbers, right? Again, that's going to allow us to not miss any cases, which is nice. But listing down all the possible 3 factorial cases, these will be the numbers. And obviously, the sum and the product would just be the same, because we're just permuting the digits. So last thing to do, simply add them up. You guys can do it on your own here, but I'm just going to tell you that if you add all those digits, all those 6 possible numbers, we're going to get the answer of 3,996. And this will be our final answer. Hopefully you guys learned something new from this video, and I'll see you in the next one. Bye bye.